What if the greatest question humanity has ever asked isn't how the universe began, but what existed before it? The Big Bang is often presented as the ultimate origin story, the explosive birth of space, time, matter, and energy itself. Every galaxy, every star, every planet, and even you are the direct result of that singular event. But when we look closer, an unsettling question emerges. If everything began there, then what came before? Was there a before at all, or does the very act of asking this question reveal a flaw in how we think about time and existence? This mystery isn't just scientific, it cuts into philosophy, mathematics, and even the way we define reality itself. To understand why this question is so haunting, consider how human beings have always searched for origins. We ask where rivers come from, where life began, where the earth formed, and with every answer, we trace the chain further back. But when it comes to the universe, the chain seems to slam into a wall, the Big Bang. According to modern cosmology, the universe expanded from a hot, dense state about 13.8 billion years ago. This was not an explosion in space, but rather an explosion of space itself. The very fabric of reality stretched outward, cooling as it expanded, eventually giving rise to stars, galaxies, and us. This story has been confirmed with overwhelming evidence. The cosmic microwave background radiation, essentially the faint afterglow of the Big Bang, still permeates space today, acting as a kind of fossil imprint of the universe's fiery youth. The expansion of galaxies away from us, as observed by Edwin Hubble, further proves that space is stretching. Even the abundance of light elements, like hydrogen and helium, matches predictions made by Big Bang nucleosynthesis. In other words, science has painted a remarkably clear picture of what happened after the beginning. But here's the catch. Science still struggles with the moment of the beginning itself. The equations of general relativity, when traced back to the earliest instant, collapse into infinities. Instead of clarity, we get a singularity, a point where density becomes infinite, and the laws of physics break down completely. It is as though the universe is hiding its own origin, refusing to give us a clear answer. And this is where the real mystery begins. Asking what came before the Big Bang is not like asking who built the pyramids or what caused the dinosaurs to vanish. Those are mysteries with potential evidence waiting to be uncovered. But with the Big Bang, we are pushing into a domain where evidence may be forever out of reach. If time itself began at that moment, then the concept of before might not even exist in any meaningful way. It's like asking what's north of the North Pole. The question dissolves into paradox. And yet, humans are not content to stop there. We want to know if there was something, a hidden reality, an earlier cosmos, a deeper framework that preceded our universe. This pursuit has spawned countless theories, ranging from the rigorously mathematical to the wildly philosophical. Physicists, cosmologists, and philosophers alike have tried to break open the mystery. Was our universe born from quantum fluctuations? Did another universe collapse, leading to ours in a grand cosmic cycle? Are we just one bubble in an infinite sea of universes? Or was the Big Bang not an absolute beginning at all, but merely a transition in a much larger, eternal reality?
What makes this question even more fascinating is how it blurs the lines between science and philosophy. Typically, physics deals with measurable, observable phenomena. But the moment we ask what came before the universe, we're forced into territory where observation may not be possible. Instead, we rely on abstract reasoning, mathematics, and deep speculation. In many ways, the mystery of what came before the Big Bang is as much about the limits of human understanding as it is about the cosmos itself. And perhaps that's why it feels so profound. Because in this single question lies an echo of our own existence. We want to know where we came from. If the Big Bang was the beginning, then what lies beneath that beginning? If there was something before, then what does that say about the true nature of reality? And if there was nothing at all, how could something, the entirety of existence, emerge from absolute nothingness? It is this tension, this gap between evidence and imagination, that makes the mystery of before the Big Bang one of the greatest intellectual frontiers of our time. In the coming explorations, we'll dive into theories that attempt to answer this question, ideas that challenge our notions of time, space, matter, and reality itself. From singularities to quantum foam, from bouncing universes to eternal inflation, from the multiverse to the possibility that our entire reality is a mathematical construct, we'll see just how vast the human imagination becomes when confronting the unknown. But before we take that journey, it's important to acknowledge something essential. No matter how advanced our science becomes, we may never know with certainty what came before. That doesn't make the search meaningless. On the contrary, it makes it more valuable because it shows us the edges of knowledge and dares us to step beyond them. When people ask what was there before the Big Bang, they usually imagine time stretching endlessly backward, like a road with no beginning. Our everyday experience reinforces that image. We wake up, live through the day, and fall asleep at night, always within the steady march of seconds, minutes, and hours. Even when we look back into history, there's always a before. Yesterday came before today, last year came before this one, and the age of dinosaurs came before humanity. But when cosmologists examine the universe, they encounter something completely alien to our intuition. Time itself may have been born with the Big Bang. If that's true, the question of what came before becomes something more like a logical trap, a question without meaning because before didn't exist at all. Einstein's theory of relativity changed the way we think about time. It showed us that time is not some invisible, universal clock ticking outside the universe. Instead, it is bound to the fabric of space itself, forming what physicists call space-time. Matter and energy warp this space-time, and that warping determines the flow of time. This means that time is not absolute, but dynamic, capable of stretching, slowing, and even stopping under certain conditions. For example, near a black hole's event horizon, time for an outside observer appears to grind to a halt. If time is flexible and dependent on the state of the universe, then it makes sense that in the moment of the Big Bang, when the universe was infinitely hot and dense, time as we know it may not have existed at all.
This is why cosmologists often compare asking what happened before the Big Bang to asking what lies north of the North Pole. The North Pole is the limit of north. Once you're there, the concept of north no longer applies. In the same way, the Big Bang may represent the boundary of time, with no before to speak of. Time did not extend infinitely into the past. Rather, it began with that event, unrolling forward in one direction. The arrow of time, which we associate with increasing entropy and the growth of complexity, was set in motion at that point. But this idea is difficult to grasp emotionally because it clashes with our human instincts. We live in a world where every effect has a cause, and every beginning feels like it must come from something earlier. The Big Bang, as the beginning of time, challenges that fundamental chain of reasoning. If time started then, it breaks the endless regression we're used to asking. What came before that cause, and what came before that? Suddenly, there is no before, only the raw fact of the universe's birth. Philosophers have wrestled with this notion as much as scientists. St. Augustine, long before modern cosmology, suggested that time itself was created with the world, and that asking what God was doing before creation was meaningless, because there was no before. In a way, modern physics echoes this same reasoning, but without invoking the divine. Instead, it tells us that time is emergent. It arose with the universe itself. This creates a fascinating tension between physics and human intuition, because even when we're told there was no time before the Big Bang, our minds still try to imagine some hidden background, some stage on which the universe suddenly appeared. Another aspect of the problem of time comes from quantum mechanics. In quantum physics, time is treated as a parameter, not a dynamic entity, unlike in relativity. Reconciling these two views of time remains one of the greatest unsolved puzzles in theoretical physics. If time itself began at the Big Bang, then what does that mean for quantum mechanics, which assumes time as part of its very equations? If there was no time before, how can we even describe the state of the universe leading up to its birth? These tensions suggest that our current understanding of time is incomplete, and that a deeper theory of quantum gravity may reveal what really happens at the boundary of the Big Bang. Some thinkers even question whether time exists in the way we think at all. According to certain interpretations, time may not be a fundamental property of reality, but a construct of human perception. In that case, the Big Bang may not have created time, but instead marked the point at which the conditions of the universe allowed beings like us to experience and measure change in a meaningful way. In other words, time may only be a way of describing relationships between events, not a physical thing that can begin or end. If this perspective is true, then asking what was before the Big Bang is like asking what the universe looks like without any observers. It may not even be a meaningful question. There's also the idea that while time as we know it began with the Big Bang, other kinds of time might exist outside our observable universe. This would mean that the Big Bang didn't start everything, but instead marked the beginning of our particular branch of time. Other branches, inaccessible to us, could stretch beyond what we can see, holding the possibility of a before in some higher dimensional sense. But within the universe we inhabit, time itself is finite, with a definite starting point. The problem of time is ultimately a clash between human intuition and the mathematics of cosmology. On one hand, our instincts demand a before, a cause behind the cause. On the other, physics seems to suggest that time is not infinite in both directions, but has a beginning. Accepting that challenges not only our scientific understanding, but our very sense of what it means for something to exist. Was the Big Bang a creation from nothing, or the start of time itself? Or is our language simply too limited to express what really happened? When scientists trace the universe's history backward using Einstein's equations, they arrive at a point of unimaginable density and heat, a singularity. This isn't just a fancy word for a very small dot of matter. It's a breakdown of everything we know about physics. At a singularity, the equations that normally describe gravity, space, and time stop working, spitting out infinities instead of meaningful answers. According to classical general relativity, this singularity marked the very beginning of the universe. All of space, time, matter, and energy were once compressed into an infinitely dense, infinitely hot state before expanding into the cosmos we see today. The singularity concept sounds straightforward at first, but the more you think about it, the stranger it becomes. Infinity is not a number. It's a signal that the math has broken down, that the theory is being pushed beyond its limits. Physicists don't actually believe that the universe was literally an infinitely small point. Rather, the singularity reveals the moment where our understanding fails. It's like a blank space on a map marked, "Here be dragons," a frontier where known physics no longer applies. To visualize what this means, consider what happens when you fall into a black hole. General relativity predicts that inside the event horizon, all paths lead inevitably toward a singularity. Matter is crushed to infinite density, and time itself ends. The Big Bang singularity is similar, but instead of being hidden inside a black hole, it's thought to be the origin of the entire cosmos. In both cases, the appearance of infinities suggests that general relativity is incomplete. We need a deeper theory, something that unites relativity with quantum mechanics, to describe what truly happens at those extremes. The singularity also raises profound philosophical questions. If the universe began as a singularity, what does that say about causality? Normally, every event has a cause, but if time itself starts at the singularity, then there is no before in which a cause could exist. The Big Bang might therefore represent a boundary, beyond which the concept of cause and effect no longer applies. This unsettles many people because it seems to deny the principle of sufficient reason, the idea that everything must have an explanation. And yet, according to our best models, the singularity is unavoidable when we push relativity to its limits. There's another layer of mystery. Singularities might not be physical at all, but instead artifacts of our incomplete mathematics. Many physicists believe that the infinities of the Big Bang are simply a sign that relativity needs to be replaced by a quantum theory of gravity. In such a theory, the singularity might vanish, replaced by a finite, describable state. Instead of a point of infinite density, the early universe could have been a very small but finite configuration, governed by quantum rules. This would mean that the singularity isn't real, but only a placeholder for new physics waiting to be discovered. Still, even as an abstract concept, the singularity has enormous importance. It forces us to acknowledge the limits of our understanding and motivates the search for a theory that unites the two great pillars of modern physics, general relativity and quantum mechanics. Without such a theory, the singularity remains a wall we cannot pass, hiding the truth about the earliest moment of existence. What makes the singularity idea even more fascinating is how it ties into the human desire for origins. We want to know where everything comes from, and the singularity seems to offer an answer. The universe started there. But when we dig deeper, we find that the singularity is not really an answer at all. It's a puzzle, a riddle that tells us we're asking the right questions, but don't yet have the language to solve them. Some scientists argue that the singularity concept should not be taken literally, but should instead be viewed as a symbol of humility. It tells us that our theories, as powerful as they are, cannot yet reach into the very beginning. Others take it as a challenge. If infinities appear, then our job is to push further, to build a framework where the universe's first moments can be described in concrete, testable terms. This is why discussions of the singularity often lead directly into more advanced theories, such as quantum cosmology, string theory, or loop quantum gravity. Each of these attempts to go beyond the singularity and describe what, if anything, lies behind it. Perhaps the singularity was never a true point of infinite density, but rather a window into a larger, richer structure of reality. In that sense, the singularity is not the end of the story, but the beginning of a new chapter in humanity's quest to understand the cosmos. At the edge of our understanding, when we try to push physics beyond the singularity, one of the most fascinating possibilities that emerges is the role of quantum fluctuations. In the smallest scales of reality, in the strange and uncertain world of quantum mechanics, nothing is ever truly stable. Even what we call a vacuum, a region of space with no matter and seemingly no energy, isn't empty at all. Instead, it seethes with activity. Particles and antiparticles pop in and out of existence, borrowing energy from nothingness for brief moments before annihilating again. This restless activity is known as quantum fluctuations, and it may hold the key to the origin of everything. To understand why, we have to shift our perspective away from the deterministic cause and effect world that our everyday lives suggest and enter the probabilistic framework of quantum theory. At this microscopic level, uncertainty rules. The Heisenberg uncertainty principle states that we cannot know both the energy and the time duration of a system with perfect accuracy. This means that energy can appear out of nowhere, as long as it vanishes quickly enough. These fluctuations happen constantly, all around us, even in the apparent emptiness of interstellar space. Now, what happens if such a fluctuation doesn't vanish? What if, instead of disappearing back into the vacuum, one fluctuation grows, expands, and takes on a reality of its own? Some physicists propose that this is exactly what our universe is, a giant quantum fluctuation that didn't collapse, a bubble that inflated into the cosmos we now inhabit. In this picture, the universe did not need a cause in the classical sense, nor did it need pre-existing matter or energy. Instead, it emerged naturally out of the laws of quantum physics, out of the restless foam of possibilities at the foundation of reality. The concept of quantum foam, introduced by John Wheeler, is particularly useful here. Wheeler suggested that on the smallest scales of space and time, at the Planck length and Planck time, space is not smooth and continuous, but wildly chaotic. It boils and froths with fluctuations, like the surface of a stormy sea. Within this foam, tiny, fleeting universes could bubble into existence. Most would disappear almost instantly, but some might persist, undergoing a runaway expansion that leads to something like our own universe. The Big Bang, in this framework, was not the absolute beginning, but the blossoming of one such bubble out of the quantum froth. This raises an extraordinary idea. The universe may be, in a sense, free. It didn't need to come from something else. It didn't need a previous world to collapse. Instead, it may be the natural result of quantum laws, which allow existence itself to appear spontaneously. As Stephen Hawking once suggested, because there is a law like gravity, the universe can and will create itself from nothing. That nothing, however, is misleading. It isn't truly nothing, but a quantum vacuum, a sea of potential. The implications are staggering. If our universe is the result of a quantum fluctuation, then the concept of nothingness itself has to be redefined. Nothing isn't a blank void of absolute emptiness. Nothing is instead a seething creative background of possibilities, capable of giving rise to everything. In this sense, the vacuum is far from empty. It is the richest, most fertile ground imaginable, because it holds within it the potential for all that exists. However, this picture also raises further questions. If the universe is a quantum fluctuation, why did it expand rather than collapse back? Here, inflationary theory offers part of the answer. In the earliest fraction of a second, a field called the inflaton may have driven exponential expansion, stretching the tiny fluctuation into a vast, smooth universe. This inflationary period could explain why the universe today looks so uniform across immense distances and why it seems flat rather than curved. Quantum fluctuations, amplified by inflation, could also explain the seeds of cosmic structure, the tiny variations in density that eventually became galaxies and stars. In other words, the same fluctuations that may have birthed the universe also shaped its destiny. Critics, however, point out that while quantum fluctuations explain how a universe could arise, they don't fully solve the question of why the laws of physics exist to allow this in the first place. If the universe emerged from quantum foam, then where did the foam come from? Are the laws of quantum mechanics eternal, existing beyond space and time? Or did they too emerge from some deeper reality? These are questions that push the boundaries of physics into metaphysics, blurring the line between scientific inquiry and philosophical speculation. Some thinkers propose that perhaps universes are constantly bubbling out of quantum foam, with most vanishing instantly, but a few inflating into full-fledged realities. If so, then our universe is not unique, but one of countless others. Each might have different physical constants, different laws, different structures altogether. This multiverse idea, born partly out of quantum fluctuation theory, challenges our sense of uniqueness and forces us to confront the possibility that the cosmos is far stranger and more diverse than we could ever imagine. And yet, there's something profoundly elegant about the notion that everything we see, the stars, the galaxies, the very atoms in our bodies, could have emerged from the restless uncertainty of the quantum vacuum. Out of fluctuations so small and fleeting they almost don't exist, came the vastness of the cosmos. In a way, this reflects a deep theme in nature: great complexity arising from simplicity, infinite richness emerging from what appears to be nothing. Still, for all its elegance, the quantum fluctuation idea remains speculative. We cannot peer back into the quantum foam before the Big Bang to confirm it. We can only infer its plausibility from what we know about the quantum world and from the patterns we see imprinted in the cosmic microwave background, the faint ripples left over from the universe's infancy. Those ripples do align beautifully with the predictions of quantum fluctuation models, giving them weight. But whether this means the entire universe literally sprang from a fluctuation remains one of the deepest questions in science. The problem, ultimately, may lie with our own language. When we say the universe came from nothing, we struggle to explain what that nothing really is. For quantum mechanics, nothing is never truly empty. It's always alive, always unstable, always fertile with potential. If that's the case, then perhaps the real miracle is not that the universe exists, but that the laws of quantum physics themselves are so generous that existence is inevitable. For centuries, humanity has wrestled with the idea of beginnings and endings. Did the universe have a first moment, or has it always existed in some form? One of the most compelling answers to this question is the idea of a cyclic universe, the possibility that the cosmos is not a one-time event, but part of an eternal rhythm of expansion and contraction, birth and death, destruction and rebirth. In this vision, the Big Bang wasn't the beginning of everything, but simply the most recent chapter in an infinite cosmic story. At its core, the Cyclic model suggests that the universe expands for billions of years, driven initially by the Big Bang. Over time, gravity begins to slow that expansion. Eventually, according to some variations of the theory, gravity wins the tug-of-war, and the universe begins to contract. Galaxies would drift closer together, stars would collide, and black holes would merge, until everything collapses back into an ultra-dense state known as the Big Crunch. From this state, a new Big Bang could erupt, giving birth to a fresh universe. This cycle could repeat endlessly, with universes arising and collapsing one after another without a true beginning or end. One of the first scientific incarnations of this idea came in the 20th century, when physicists began exploring models that included a Big Crunch. If the density of matter in the universe were high enough, its gravity would eventually halt the expansion detected by Hubble and reverse it. For decades, scientists debated whether the universe's density was enough to ensure eventual collapse. If so, the cyclic model would be a natural outcome. In such a universe, the Big Bang would not be the start of time, but just the latest bounce in an infinite sequence. However, new discoveries complicated this picture. In the late 1990s, astronomers studying distant supernova discovered that the universe's expansion isn't slowing down, it's accelerating. This acceleration is attributed to dark energy, a mysterious form of energy that seems to push space apart. If this acceleration continues indefinitely, the universe will never collapse. Instead, it will expand forever, becoming colder and emptier with time. This heat-death scenario appears to challenge the traditional cyclic model. After all, if the cosmos expands endlessly, there will be no contraction, no Big Crunch, and no rebirth. Yet scientists have not abandoned the cyclic idea. Instead, they've reformulated it in new and fascinating ways. One approach combines the cyclic model with the discovery of dark energy. Instead of the universe collapsing, each cycle could be driven by the properties of dark energy itself, creating repeated phases of expansion and renewal. For example, in some versions of string theory, our universe exists on a three-dimensional brane, floating in a higher dimensional space. If another brane collides with ours, the energy from the collision could create something that looks like a Big Bang. These collisions could happen cyclically, each one birthing a new universe, even as time itself stretches infinitely backward. Other models, like those explored in loop quantum cosmology, propose that quantum effects prevent the universe from collapsing into a true singularity. Instead, when it reaches a minimum size, quantum gravity forces cause it to bounce outward again. In this view, each cycle is not an exact repetition, but an evolution. The universe doesn't repeat itself perfectly like a film loop, but rather grows and changes with each bounce, potentially producing different structures, constants, or even laws of physics over time. This paints a picture of a universe that is both eternal and dynamic, always reinventing itself. The cyclic model is also philosophically appealing because it sidesteps the need for an absolute beginning. If the universe has always gone through cycles, then there is no need to explain a moment of creation. The question, what came before the Big Bang, becomes unnecessary because the Big Bang was always preceded by another universe. The cosmos simply is, eternal, oscillating, and unending. This vision has a kind of poetic symmetry, an infinite heartbeat of creation and destruction. Of course, this raises deeper questions. If the universe truly cycles forever, does anything carry over from one cycle to the next? Are we living in a universe that remembers its past, or is each new cycle a complete reset? Some theorists suggest that entropy, the measure of disorder, might increase with each cycle. If true, then the cycles wouldn't be perfectly identical. They would evolve toward greater complexity. Others propose that entropy could somehow be reset, allowing each cycle to begin fresh, free of the clutter of the past. This remains one of the great mysteries of cyclic cosmology. The idea of an eternal cyclic universe also forces us to rethink the nature of time itself. In a one-time Big Bang model, time begins with that event. But in a cyclic universe, time stretches infinitely in both directions. There was always a before, and there will always be an after. This is deeply unsettling to some, because it means that our universe is just one moment in an endless chain, not a singular, unique creation. Yet it is also deeply comforting to others, because it suggests that the cosmos is eternal, that creation is never-ending, and that the universe will always find a way to renew itself. Despite its elegance, the cyclic model is still speculative. We lack direct observational evidence of previous cycles, and the accelerating expansion of the universe presents challenges. But the very fact that cosmologists are exploring it shows how determined we are to break through the mystery of beginnings. Whether or not the cyclic universe is real, it offers a powerful reminder that our imagination, like the cosmos, refuses to be contained. In the end, the cyclic model reminds us of something profound, that even destruction may not be the end. In the heart of collapse lies the seed of rebirth. The Big Bang might not have been the singular beginning of all things, but rather the latest breath in an eternal cosmic rhythm. The bounce hypothesis takes the idea of a cyclic universe one step further by suggesting that what we see as the beginning of our universe may not have been a true beginning at all, but rather the aftermath of a collapse and rebound. In this view, the universe didn't emerge from nothingness at the Big Bang, but instead from the death throes of a prior cosmos. Instead of a singularity that signals the end of physics, the collapse of that earlier universe reached an extreme state of density and energy, and then rebounded outward in what we perceive as our Big Bang. This framework essentially reimagines the birth of our universe not as creation ex nihilo, but as a transformation, an oscillation from contraction to expansion. The notion of a cosmic bounce arises largely from the limitations of classical general relativity. If Einstein's equations are taken at face value, the collapse of a previous universe should indeed lead to a singularity, a point of infinite density where the laws of physics no longer function. But when physicists try to blend general relativity with quantum mechanics, specifically in approaches like quantum gravity or loop quantum cosmology, the singularity is softened. Rather than hitting an infinite wall of density, the universe approaches an ultra-compressed quantum state. And in some of these models, that state has a built-in resistance to further compression. Just as quantum mechanics prevents electrons from collapsing into atomic nuclei due to quantum pressure, there may be a quantum form of gravity that prevents the cosmos from reaching a true singularity. Instead of ending, the universe bounces back into expansion. Visualizing this, imagine the universe as a balloon being inflated and deflated. In the standard Big Bang model, the balloon starts empty, is suddenly inflated, and continues expanding forever. In the bounce model, however, the balloon has always been expanding and contracting in some form. One phase of deflation leads to maximum compression, but rather than vanishing, it rebounds into a new expansion. Our current expanding universe, then, could simply be the latest iteration in a timeless chain of cosmic oscillations. The mathematics behind the bounce hypothesis comes most prominently from loop quantum cosmology, an application of loop quantum gravity. This theory attempts to quantize space-time itself, suggesting that space is not infinitely divisible, but made up of discrete chunks, like pixels on a screen. At extremely small scales, on the order of the Planck length, space cannot shrink beyond a certain limit. That introduces a natural cutoff, preventing densities and energies from reaching infinity. When applied to cosmology, this means the Big Bang singularity is replaced by a big bounce. At the moment of maximal compression, quantum geometry creates a repulsive force that drives the universe to expand again. There's a profound philosophical elegance to this idea. It suggests that the universe has no true beginning or end, but instead oscillates eternally between expansion and contraction. Each cycle wipes away much of the evidence of the prior one, but subtle imprints might survive in the form of patterns in cosmic radiation or structures in space-time itself. In fact, some cosmologists have proposed that anomalies in the cosmic microwave background, the faint afterglow of the Big Bang, could be signs of events from before our universe's expansion, faint whispers of a time before time as we know it. However, the bounce hypothesis is not without challenges. One of the main difficulties lies in entropy, the measure of disorder in a system. If each bounce resets the universe, what happens to entropy across cycles? Thermodynamics tells us that entropy should always increase, which means that successive cycles would become longer and larger, as each new universe inherits more disorder than the last. Eventually, this would lead to universes that are infinitely stretched out and unable to collapse again. Some versions of cyclic models try to resolve this by proposing mechanisms through which entropy is shed or recycled during contraction, but this remains an area of ongoing debate. Another complication is the observational challenge. If a bounce occurred, can we actually detect its fingerprints? Most of the evidence from before the Big Bang, if there was a before, would have been erased or stretched beyond recognition during the rapid expansion of inflation. But theorists are hopeful that certain features of primordial gravitational waves or subtle irregularities in the cosmic microwave background might one day provide supporting evidence. Until then, the bounce remains an intriguing but unverified concept. If the bounce hypothesis is correct, it has staggering implications for our place in the universe. It means that everything we see, the galaxies, stars, planets, and even ourselves, is not the product of a singular, once-in-a-lifetime event, but part of an ongoing cycle that stretches back into an unfathomable past. Our Big Bang might not have been the first, nor will it be the last. The universe may have collapsed countless times before, and may collapse and rebound countless times again. In this light, the cosmos becomes not a fragile, one-time occurrence, but a robust and enduring process, forever creating and recreating itself. The bounce hypothesis doesn't answer every question. It still leaves open what laws govern these cycles, whether they go on eternally, and what ultimate reality lies beneath them. But it provides a strikingly different way to think about origins. Instead of asking, what was before the Big Bang? The bounce invites us to consider that there may never have been a true beginning at all. What we call the beginning may be just another turn in an endless dance of cosmic rebirth, with no first note and no final silence, only the rhythm of eternity. Eternal inflation takes the already strange concept of inflation and stretches it into something almost unthinkable. In standard inflation, the universe expanded at an incomprehensibly fast rate in the tiniest fraction of a second after the Big Bang. This rapid swelling smoothed out space, made it uniform, and set the stage for the universe we inhabit. But eternal inflation suggests that this process never really ended everywhere. Instead, while inflation stopped in certain regions, allowing them to cool and form stars, galaxies, and eventually us, it continued in other regions. That means the universe is not a single expanding bubble,
but rather an endless froth of bubbles, each one its own universe, each possibly with different physical laws, constants, and histories. Our Big Bang, then, was not necessarily the beginning of everything, but simply the beginning of our bubble. Outside of it, inflation continued, bubbling new universes into existence endlessly, creating what cosmologists call a multiverse. In this picture, what we call the universe is really just one island in a vast and perhaps infinite cosmic ocean, surrounded by countless other universes we can never see or touch. Some might resemble ours, with galaxies, stars, and planets. Others could be utterly alien, perhaps governed by completely different rules of physics. This idea changes the meaning of the question, what was before the Big Bang? Because it reframes the Big Bang not as a universal birth, but as a local event. Our Big Bang was simply the moment our bubble universe pinched off from the inflating sea. There may never have been a before in the sense of one universal timeline, because inflation is eternal in some directions. Instead, there could be infinite beginnings, infinite creations, each bubbling into being, each with its own version of space and time. Eternal inflation also introduces strange possibilities. If inflation creates universes endlessly, then statistically speaking, every possible kind of universe might exist somewhere. That means universes where stars never form, universes where physics prevents stable atoms, universes where life evolves in forms beyond imagination. In fact, some cosmologists argue that even universes almost identical to ours could exist, so similar that there might be another version of you living in a nearly identical history, differing only by the smallest of details. But eternal inflation is not without its puzzles. One of the biggest challenges is that it may not be testable in the usual scientific sense. If other universes are completely sealed off from ours, beyond our cosmic horizon, then we may never be able to observe them directly. Yet some speculate that tiny signatures could remain, such as scars in the cosmic microwave background from collisions between bubble universes. If found, these would be the first observational evidence that we are not alone in the multiverse.
What eternal inflation ultimately suggests is that our Big Bang was not the ultimate beginning, but just one of countless beginnings embedded in an endlessly expanding multiverse. It makes the question of what was before the Big Bang almost misleading, because the answer may be that there was no singular before, but rather an infinite ongoing process of creation where bubbles of universes are born forever. This doesn't just push the edge of physics, it challenges the very way we think about reality, identity, and even existence itself. When considering what may have existed before the Big Bang, the discussion often leads into the territory of the multiverse, a concept that has captivated physicists and philosophers alike. The multiverse proposes that our universe is not the only one, but merely one of countless others, each potentially governed by different physical laws, constants, and dimensions of reality. Within this framework, the Big Bang that gave rise to our cosmos may not have been the unique birth of everything, but just one occurrence within a vastly larger reality that extends beyond what we can ever directly observe. This idea challenges the long-standing assumption that the universe is all there is, replacing it with a vision of endless variety and boundless complexity. There are several models of the multiverse, each offering a different explanation for how multiple universes could exist and how they might connect to the question of what preceded our own beginning. One of the most widely discussed models arises directly from the idea of eternal inflation. In this view, while inflation stopped in our region of space, giving rise to our Big Bang and eventual galaxies, it continues endlessly elsewhere. Each bubble of space that stops inflating becomes its own universe, with its own Big Bang-like event and its own history. Our universe is one bubble, but there could be an infinite froth of universes forming eternally in the inflating background, a multiverse without end. Another version of the multiverse is sometimes called the brain world scenario, derived from string theory. In this framework, our universe exists as a three-dimensional brain floating in a higher dimensional space. Other brains could exist parallel to ours, each with its own physics. Collisions between brains could even trigger Big Bang-like events, suggesting that the birth of our universe may have been caused by such an interaction. This concept not only provides a possible explanation for the origin of our cosmos, but also suggests that countless other universes, inaccessible yet real, coexist with ours in higher dimensions. Quantum mechanics also inspires another type of multiverse, often referred to as the many worlds interpretation. According to this idea, every quantum event branches reality into multiple outcomes, creating a near infinite tapestry of universes where every possibility is realized. While this version of the multiverse is more about parallel realities branching off continuously rather than universes emerging from a singular Big Bang event, it still plays into the larger theme that our cosmos is just one thread in a vastly larger fabric. Some models even imagine a mathematical multiverse where every logically possible universe exists, whether or not it can ever be physically realized. In this radical vision, reality itself is not a singular structure, but a limitless ensemble of all conceivable realities, each following its own rules. Our universe, with its finely tuned constants and laws, would simply be one instance among an endless collection, and the fact that it permits life might not be special at all, but merely inevitable when considering the sheer vastness of possibilities. All of these multiverse models, though wildly different in their construction, share one underlying implication. The Big Bang may not have been the beginning of all things. Instead, it might have been just a local event within a larger, eternal, and infinitely varied backdrop. If such a multiverse exists, then asking what came before the Big Bang becomes less about finding a singular cause and more about recognizing that there may never have been a true beginning. What we call the universe could be one chapter in a book with infinite pages, each universe born, evolving, and perhaps dying, while countless others exist simultaneously beyond our view.
Yet, this concept also raises profound challenges. If other universes exist but remain forever beyond our ability to observe or measure, are they part of science or philosophy? Can physics legitimately discuss realms that no experiment could ever reach? These questions highlight the difficulty of studying the multiverse. On one hand, it provides a way to explain why our universe has the properties it does. But on the other hand, it threatens to drift into speculation unmoored from empirical testability. Still, the multiverse remains one of the most intriguing answers to the mystery of what preceded our universe. It reframes the question entirely. Perhaps there was no singular before, but instead a timeless expanse in which universes are constantly emerging, colliding, and branching. In that grander landscape, the Big Bang was not the birth of existence itself, but merely the opening of our own small window onto an infinite reality. String theory offers one of the most ambitious attempts to unify all of physics under a single framework, and when applied to cosmology, it gives rise to some of the most exotic possibilities for what might have existed before the Big Bang. In everyday physics, we think of matter as being made of point-like particles, electrons, protons, photons, tiny dots that have no internal structure. But string theory replaces these points with unimaginably small vibrating strings of energy. Each vibration corresponds to a different particle, meaning that the diversity of matter and forces we observe could simply be different notes played on the same fundamental string. This elegant idea doesn't stop there. It requires extra dimensions of space to work consistently. Instead of the familiar 3 dimensions of length, width, and height, string theory often involves 10 or 11 dimensions, most of them curled up so tightly that we don't perceive them. When cosmologists explore what this means for the universe's beginning, they encounter a picture that's very different from the traditional singularity. One of the leading models that emerges from string theory is called brane cosmology, derived from the word membrane. In this view,
Our universe is not the whole of existence, but just a three-dimensional surface, or brain, floating within a higher dimensional space known as the bulk. Imagine a sheet of paper suspended in the air. That sheet is like our universe, and there may be countless other sheets parallel to ours, each with its own laws, particles, and possibly its own Big Bang events. The truly fascinating part is what happens when these brains interact. If two brains collide in the higher dimensional bulk, the energy released could manifest as a Big Bang, igniting an entire universe like our own. This leads to the scenario known as the ekpyrotic universe, inspired directly by string theory. Instead of the universe beginning from nothing or from a singular point, it begins from the crash of two massive brains. The energy of the collision creates the hot, dense conditions we associate with the Big Bang, but crucially, it avoids the paradox of a singularity where physics breaks down. The ekpyrotic model also dovetails neatly with ideas of cyclic universes. Brains could collide over and over again, creating multiple cycles of expansion and contraction. In this view, our universe may not be the first or the last, but simply one round in an endless sequence of brain collisions, each separated by trillions upon trillions of years. What makes this perspective especially compelling is that it preserves some of the successes of inflation, while also offering a different explanation for cosmic uniformity. In the ekpyrotic model, the conditions leading up to the collision naturally smooth and flatten space, providing a reason why the universe looks so uniform without requiring an extremely rapid inflationary phase. This could, in principle, leave traces in the cosmic microwave background, the faint afterglow of the Big Bang, that we might one day be able to measure. String theory also allows for even wilder speculations. Since it requires extra dimensions, those dimensions might play an unseen role in shaping our cosmos. The curled-up shapes of these hidden dimensions, known as Calabi-Yau manifolds, could determine the values of fundamental constants, like the strength of gravity or the charge of the electron. This means that in other universes, other brains floating in the bulk, those constants could be different. Entirely different laws of physics could prevail, with some universes unable to form atoms, let alone stars or life, while others might host structures beyond our imagination. If brain collisions can create Big Bangs, then the bulk itself might be teeming with universes, each with different physical realities. Another perspective from string theory is the concept of the string landscape. In this view, there are not just a few possibilities for how the extra dimensions could be configured, but an almost unimaginably vast number, possibly 10 to the 500 different vacuum states. Each vacuum state corresponds to a different universe with its own set of physical constants. Our universe is then just one point in this vast landscape, selected either by chance or by some deeper principle we do not yet understand. If this picture is true, the question of what came before the Big Bang shifts into an even larger one. Why does our universe exist in this particular form among such a vast array of possibilities? String theory even provides ideas that resonate with quantum fluctuations. In certain scenarios, the universe could emerge from a quantum tunneling process in the higher dimensional bulk. Instead of arising from nothing, the universe would tunnel from one vacuum state to another, creating a new brain and igniting a new cosmos. This connects the string landscape with the eternal inflation picture, painting a reality where universes endlessly sprout, collide, and evolve within an infinite multiverse. But as fascinating as all this sounds, it is important to emphasize that these ideas remain deeply theoretical. String theory itself has not yet been proven experimentally. The extra dimensions it requires are so small that we cannot detect them directly with current technology, and brain collisions, if they occur, would take place on scales and energies far beyond what we can reproduce in laboratories. Still, researchers search for indirect evidence, patterns in the cosmic microwave background, subtle gravitational waves, or even unexpected particle physics results. That might give us hints. If true, the string theory perspective fundamentally reshapes how we think about the Big Bang. No longer is it a singular, inexplicable event marking the absolute beginning of everything. Instead, it becomes a transition point, one collision or fluctuation among countless others in a vast, higher dimensional reality. Our universe would be just a chapter in an eternal, multidimensional story, and the true beginning may be forever beyond our reach, or may not exist at all. The Big Bang, then, is not the ultimate origin, but the latest spark in an endless cosmic dance of brains and strings, where creation is not a one-time miracle, but a recurring rhythm written into the fabric of higher dimensional space. Loop quantum gravity offers one of the most intriguing alternatives to both classical general relativity and string theory when it comes to thinking about what could have existed before the Big Bang. At its core, the idea stems from the realization that general relativity describes space and time as a smooth, continuous fabric. But when you push this framework down to unimaginably tiny scales, close to the Planck length, it begins to falter. Quantum mechanics tells us that the smallest scales of reality should be filled with uncertainty, fluctuations, and discrete units, rather than infinite smoothness. Loop quantum gravity, or LQG for short, tries to unify general relativity with quantum mechanics by proposing that space itself is not continuous, but made up of finite, discrete building blocks, like a fabric woven from tiny threads rather than a single continuous sheet. This shift in perspective has dramatic implications for the Big Bang. In the standard picture based on general relativity, when you trace the universe backward in time, the density of matter and energy becomes infinite. All of space collapses into a single point of infinite curvature, and you arrive at a singularity. At this point, the laws of physics break down, and we can no longer meaningfully talk about what happened before. But if space and time themselves are quantized into indivisible atoms of geometry, then you never truly reach a singularity. Just as water cannot be compressed indefinitely, because eventually you reach the molecular level, space-time in loop quantum gravity cannot collapse beyond a certain smallest unit. The equations that govern LQG suggest that instead of a singularity, the universe would undergo a bounce. This leads directly to the concept of a big bounce. Instead of beginning from nothing, the universe could have originated from the collapse of a previous cosmos. As it contracted, densities increased, but rather than reaching an infinite crunch, quantum effects created a kind of repulsive force at incredibly small scales. This quantum gravity repulsion acted like a spring, reversing the collapse and triggering an expansion, the Big Bang as we know it. In this view, the Bang is not the absolute beginning, but rather a transition from one phase of the universe to another, made possible by the granular nature of space-time itself. The implications of this are profound, because it not only offers a way to avoid the troubling infinities of singularities, but also provides a framework where, before the Big Bang, actually makes sense. If the Big Bang was really a bounce, then there must have been a contracting universe before ours. That prior cosmos could have had its own galaxies, stars, and perhaps even life, though it's unlikely anything from that phase would survive the transition. Each bounce wipes away much of the structure, but some subtle traces, like imprints in the cosmic microwave background radiation, might persist. Researchers working on loop quantum cosmology, a specialized application of loop quantum gravity to the entire universe, have tried to model this mathematically. The results show that under certain conditions, a collapsing universe doesn't end in a singularity, but rebounds. In fact, the equations predict that time continues seamlessly across the bounce. This means that the flow of events isn't annihilated at the Big Bang. Instead, the arrow of time extends beyond it, potentially forever in both directions. The Big Bang becomes a bridge, not a wall. Some versions of the theory suggest that the universe could be cyclic, with endless bounces happening one after another, though not always identical. Each cycle might see different physical constants or slightly altered conditions. If true, then our universe is just one chapter in an infinite cosmic story, one act in an eternal play of expansion, contraction, and rebirth. Unlike the traditional cyclic models based on classical physics, where entropy would build up and eventually doom the cycles to heat death, quantum gravity effects could, in principle, reset the entropy with each bounce, allowing the story to continue indefinitely without winding down. There's also an interesting consequence for our understanding of time itself. In general relativity, time is woven inseparably with space. But in loop quantum gravity, because the fundamental building blocks are discrete, time may not be a smooth river flowing endlessly, but rather a sequence of quantum ticks emerging from deeper structures. Some interpretations even suggest that time itself is not fundamental at all, but arises from the relationships between quantum states of geometry. If so, then what we call before the Big Bang might not be about tracing a clock backward, but about asking what kinds of quantum configurations preceded the state that exploded into our expanding universe. Evidence for this remains elusive, but researchers are hunting for subtle signatures. For example, the cosmic microwave background, the faint glow left behind from the early universe, could contain anomalies that hint at pre-Big Bang structures. If the universe truly bounced, there may be residual patterns imprinted during the contraction phase that survived into the expansion phase. These would look like tiny irregularities or unexpected correlations in the microwave background radiation. Detecting them would be a monumental discovery, offering a window into a time before time, into a universe before our own. Loop quantum gravity also distinguishes itself from string theory by being background independent. This means it doesn't assume space-time exists in advance, but instead tries to show how space-time itself arises from deeper, non-spatial, non-temporal entities. In some sense, asking what came before the Big Bang might be like asking what comes before space and time themselves. The bounce scenario offers a partial answer. Before our expansion, there was contraction. But it also raises deeper questions. What is the fundamental reality that produces these cycles? What are the atoms of geometry made of? Are they ultimate, or do they emerge from something even deeper?
The philosophical implications of LQG's bounce are staggering. If it's correct, then the universe may not have had an ultimate beginning, nor may it ever have an ultimate end. Instead, existence could be eternal, with each phase birthing the next. This dissolves the mystery of what caused the universe to appear from nothing, because it never truly did. It has always been in some form, transitioning endlessly between expansion and contraction. For those troubled by the idea of creation ex nihilo, loop quantum gravity provides a vision of continuity, a cosmos without a first cause, sustained by the quantum architecture of reality itself. And yet, despite the elegance of these ideas, we must be cautious. Loop quantum gravity is still an incomplete theory. It lacks experimental confirmation, and many details about how exactly the bounce would unfold remain speculative. Competing theories, like string theory and eternal inflation, offer very different visions of what came before the Big Bang. The beauty of modern cosmology is that it allows us to explore these rival possibilities, all while acknowledging that the evidence may eventually select one path over the others, or perhaps reveal something none of us have yet imagined. When we turn our attention to the question of nothingness, we find ourselves walking a tightrope between science, philosophy, and even metaphysics. The nothingness hypothesis attempts to grapple with the most basic question of all. If the universe came into being, then what was there before? Could there truly have been absolute nothing? Or is nothing itself an illusion, a human construct that breaks down under scrutiny? In everyday language, when we say nothing, we usually mean emptiness, a room with no furniture, a blank canvas, an empty void in space. But even those examples aren't true nothing. An empty room still has walls, air, space, temperature. A blank canvas still has physical matter. Even a vacuum in space still contains quantum fields, virtual particles, and fluctuations that can pop in and out of existence. The philosophical notion of absolute nothing would be the complete absence of everything. No space, no time, no laws, no quantum fields, not even the potential for existence. But immediately, we encounter a paradox. If there truly were such a state, then how could anything ever arise from it? Some philosophers argue that absolute nothing is impossible. By definition, if nothing exists, there would be no laws, no mechanisms, no processes. Without those, nothing could ever transition into something. The existence of our universe suggests that nothing was never truly the case, that there was always at least some kind of potential, structure, or foundation that allowed something to emerge. Others counter this by saying that perhaps we are mistaken in thinking of nothing as a state. Perhaps nothingness is simply meaningless, an incoherent concept when applied to existence itself. From the perspective of modern physics, nothing is not as empty as it sounds. The vacuum of space is alive with energy and uncertainty, thanks to quantum mechanics. Virtual particles pop in and out of being, fleetingly borrowing energy from the vacuum before annihilating each other. This quantum foam, or vacuum energy, suggests that what we often think of as empty space is actually seething with hidden activity. In this view, the universe could emerge from fluctuations within this quantum backdrop. But then the question shifts. If space and quantum fields always existed, then is that not already something? Philosophers have long wrestled with the ancient paradox. Why is there something rather than nothing? Some suggest that nothingness is unstable, that something is the default because it is inevitable. If absolute nothing is impossible, then perhaps the existence of the universe, or many universes, is simply the only possible reality. On the other hand, some argue that our human minds cannot even conceive of true nothingness. Every time we try, we imagine emptiness or void, but with subtle assumptions, like imagining a dark space, which is still space. If that's the case, then perhaps nothingness isn't just impossible. It's an incoherent concept we can't even imagine correctly. Certain cosmological theories attempt to resolve this puzzle by sidestepping the problem altogether. Eternal inflation, for instance, posits that universes are constantly bubbling into existence out of a larger multiverse. In this scenario, our universe did not emerge from nothing, but from a pre-existing inflationary field that has always existed in some form. The cyclic universe models suggest that there is no true beginning or end, but rather an endless loop of expansion and contraction. String theory brings forth the idea of higher dimensional brains colliding, creating big bangs as byproducts. In all of these ideas, nothing never enters the picture at all. There is always something before. Still, some physicists and philosophers seriously entertain the possibility of a true nothingness. One line of thought is that the laws of quantum mechanics themselves might allow the spontaneous creation of a universe from nothing, without cause or precondition. Lawrence Krauss, for instance, has argued that in the framework of quantum field theory, a universe can arise from nothing, because nothing itself is unstable under quantum rules. But critics quickly point out that Krauss's nothing still involves quantum fields and laws of physics. It is not absolute nothing, but rather a stripped-down something. The philosophical side adds another layer of intrigue. Some argue that even if we could conceive of true nothingness, it might not be the absence of all things, but the absence of distinctions. In other words, nothingness could be thought of as a state where there is no difference between existence and non-existence, no separation, no structure. This kind of meta-nothingness would be beyond our categories of thought, beyond language. In that case, asking what came before the Big Bang might be like asking what's north of the North Pole. The question dissolves because it assumes a framework that doesn't apply. This leads us back to the haunting possibility that our very attempt to answer the question is flawed. Maybe the universe doesn't need a cause. Maybe something is the default, and the existence of reality doesn't require an explanation in terms of nothingness. Or maybe the truth is that nothingness, as humans imagine it, cannot exist at all. And yet, the mystery persists. We exist. Our universe exists. The laws of physics operate. Time flows. And behind it all lurks this deep question. Could it all have arisen from nothing, or is nothingness itself an illusion? This is one of those problems where the boundary between science and philosophy blurs almost completely. While cosmologists search for mathematical models that describe the origins of the universe, philosophers remind us that the very language of nothingness may be misleading. Perhaps in the end, the question is less about what nothingness is and more about whether asking it even makes sense. Did nothing ever exist? Or has there always been some kind of structure, however strange, that makes something inevitable? These are the kinds of questions that stretch our imagination to its limit, pushing us to confront not just the mysteries of the cosmos, but the limits of thought itself. One of the more fascinating attempts to explain what may have given rise to the Big Bang focuses on vacuum energy, a concept that lies at the intersection of quantum mechanics and cosmology. At first glance, the term vacuum suggests emptiness, the complete absence of matter, radiation, and even energy. But quantum physics has overturned that intuition, revealing that the vacuum is not a true void at all. Instead, it is a seething, restless background field full of activity, where particles and antiparticles constantly flicker into and out of existence, borrowing energy from uncertainty itself before annihilating almost instantly. This strange phenomenon is the result of what's known as the Heisenberg uncertainty principle, which allows brief violations of energy conservation on tiny timescales. In other words, even the emptiest possible space is never truly empty. It is filled with what physicists call zero-point energy, the lowest possible energy state of a system. And it is within this restless nothing that is something that some scientists see the seeds of the universe. The idea here is that the birth of the universe could have been triggered by a fluctuation in this quantum vacuum. While most fluctuations are minuscule and disappear as quickly as they appear, under certain conditions, one could inflate to cosmic scales. Think of it like a bubble forming in boiling water. Most bubbles rise and pop, but occasionally one expands, persists, and changes the entire surface. In the cosmological analogy, one such fluctuation could have swelled rapidly, driven by the vacuum energy itself, until it underwent a runaway process we now recognize as cosmic inflation. That inflation smoothed and expanded the early universe, eventually cooling into the stars, galaxies, and cosmic web we observe today. This would mean that our universe is essentially a quantum fluctuation writ large, a temporary disturbance in the vacuum that never popped, but instead became everything. One of the most intriguing aspects of vacuum energy theories is their natural connection to dark energy, the mysterious force currently accelerating the universe's expansion. Dark energy, in its simplest form, can be thought of as vacuum energy operating at a cosmic scale, a residual energy density that pervades space itself. If this interpretation is correct, then the very energy that may have triggered the Big Bang still lingers around us, dictating the fate of the universe billions of years later. But this leads to one of the biggest puzzles in modern physics, known as the cosmological constant problem. When physicists calculate the expected amount of vacuum energy from quantum field theory, the predicted value is staggeringly larger than what is observed, off by as much as 120 orders of magnitude. This is considered one of the worst mismatches between theory and observation in all of science. If vacuum energy can indeed explain both the birth of the universe and its accelerating expansion, why is its measured strength so incredibly small compared to what equations suggest? The vacuum energy idea also raises questions about inevitability. If the vacuum is inherently unstable and prone to fluctuations, then perhaps the creation of universes is not a rare accident, but an unavoidable outcome of the underlying laws of quantum mechanics. In this view, Our Big Bang was not a one-off miracle, but one instance in a vast sea of universes, each bubbling up out of the quantum vacuum under different conditions. This possibility ties directly into multiverse theories, suggesting that vacuum fluctuations are not just responsible for our reality, but countless others as well. Each bubble might have its own laws of physics, its own constants, and its own unique cosmic evolution, making our universe just one expression of a deeper, endlessly creative quantum reality. Yet, as appealing as this sounds, vacuum energy theories also face profound conceptual challenges. For one, it is not clear what came before the fluctuation that created our universe. If the vacuum itself existed prior to the Big Bang, does that mean space-time itself existed? Or is the vacuum an abstract field beyond time and space, which somehow spawned both when the fluctuation occurred? If so, how can something like a field exist without the backdrop of space and time? These questions push against the limits of our understanding, highlighting the difficulty of using language and models rooted in our universe to describe a condition outside of it. Philosophically, the vacuum energy idea also redefines what we mean by nothing. When cosmologists say the universe came from nothing, they often mean it came from a quantum vacuum. But this is not nothing in the everyday sense. It is a structured, law-governed state with latent potential. Critics argue that this stretches the definition of nothingness to the breaking point. After all, if there are quantum fields, physical laws, and the possibility of fluctuations, then that is already a kind of something. In this view, the vacuum energy explanation might push the ultimate question one step back rather than truly resolving it. Why is there a quantum vacuum with the ability to fluctuate instead of nothing at all? Nonetheless, the vacuum energy hypothesis remains one of the most scientifically grounded proposals for how the Big Bang could have occurred. It is built on well-established quantum principles and ties neatly into observations of dark energy. While it doesn't eliminate all mysteries, it offers a framework where the origin of the universe is not an arbitrary singularity event, but a natural outgrowth of the quantum fabric itself. The challenge now is to refine our understanding of vacuum energy, reconcile theory with observation, and determine whether this restless sea of invisible fluctuations truly holds the answer to the ultimate question of cosmic beginnings. When we turn to the notion of what happened before time began, we are confronted with one of the most paradoxical questions in all of cosmology. On the surface, it seems simple. What came before the Big Bang? But the deeper you dig, the more it becomes clear that the very structure of the question may be flawed. That's because, according to many interpretations of modern physics, time itself may not have existed before the Big Bang. The Big Bang, in this view, wasn't just the origin of space, matter, and energy. It was also the beginning of time itself. To ask what was before might be akin to asking what is north of the North Pole. The question ceases to have meaning once you realize the coordinate system breaks down at its edge. This idea arises directly from the equations of general relativity, which ties space and time together into a single fabric called space-time. In this framework, the Big Bang represents not an explosion inside of time, but the very creation of time as a dimension. If time began with the Big Bang, then there was literally no before in the way we typically imagine. There was no ticking cosmic clock waiting for the event to happen. Time itself emerged at that moment. To human minds, trained to think in terms of past, present, and future, this concept is extraordinarily hard to grasp. But it may be the ultimate answer to why asking about before is a category mistake. Stephen Hawking often explained this through analogy. In his no boundary proposal, he compared the universe to the surface of the Earth. The Earth's surface has a finite area, but it has no edge where it abruptly ends. You can travel around the globe indefinitely, and while the Earth is finite, there is no boundary where it stops. Similarly, time may be finite in extent. It had a beginning with the Big Bang. But that beginning is not like a sharp edge. It is simply the point where the concept of before loses coherence. Just as you cannot stand at the North Pole and meaningfully walk farther north, you cannot go to the Big Bang and meaningfully talk about earlier times. Time as a concept stops being valid at that boundary. Still, this perspective has led to countless debates between physicists, cosmologists, and philosophers. On one hand, it provides a neat resolution. The universe has no before, so the question dissolves itself. But many argue this feels unsatisfying. If time began at the Big Bang, does that mean the Big Bang was uncaused? Does it mean the universe spontaneously popped into existence with no antecedent reality? Or does it mean there is some deeper framework beyond our current conception of time, where notions of causality still hold, but in ways that we cannot yet comprehend? Some scientists have tried to stretch our notion of time beyond the classical understanding. Perhaps the Big Bang was the beginning of time as we experience it, but not of every kind of time. Maybe there exists a meta-time, a deeper dimension where universes begin and end, while our universe only experiences a local timeline that started with its own birth. Others have proposed that time may be emergent rather than fundamental. In this sense, time is not an inherent backdrop to reality, but something that arises from the entanglement of quantum states or the statistical behavior of particles. If time is emergent, then asking about before the Big Bang may be like asking what water is before molecules of H2O arrange themselves into liquid. It is a question that loses meaning outside the context in which the phenomenon arises. In this debate, philosophy has played just as big a role as physics. For centuries, thinkers have asked whether time must have always existed or whether it could have a beginning. Aristotle argued that time is eternal, that there can be no before time. These ancient musings echo eerily in modern physics discussions. We may dress them up with quantum mechanics and relativity, but at their core, they are the same puzzles humans have wrestled with for millennia. The difficulty comes from the way our minds are wired. We instinctively think in terms of cause and effect, and we naturally extend that into a timeline. If event A happens, it must have followed something else, event B, before it. Our entire cognition is built around that causal framework. But the Big Bang forces us to consider the possibility that causality as we know it may not apply to the universe as a whole. The beginning of time itself might be a boundary that resists further explanation, not because the answers are hidden from us, but because the question itself no longer applies. And yet, the yearning for answers pushes scientists to search for models that avoid this absolute beginning. Some explore the idea of cyclic universes or quantum bounces that allow for a before. Others, like the no-boundary proposal, are content with the idea that there is no before to discuss. In either case, the question of what happened before the Big Bang continues to fuel human curiosity, not because we expect easy answers, but because it challenges the deepest assumptions we have about reality. If time began at the Big Bang, then the universe has always existed for as long as time has existed. There was no waiting, no empty stretch of eternity before it. From the perspective of time itself, the Big Bang was not an event in time, but the origin of time. That realization forces us into a strange conclusion. Perhaps the best answer to what was before the Big Bang is nothing, not in the sense of an empty void, but in the sense that the question ceases to make sense. Time itself was born in that instant, and everything, including our very act of questioning, must remain inside it. The idea that our universe could have been born from a black hole in another universe is one of the most fascinating and radical proposals about what might have existed before the Big Bang. To understand this concept, we first have to consider what a black hole really represents. In Einstein's general theory of relativity, a black hole forms when a massive star collapses under its own gravity, compressing matter into an infinitely dense point known as a singularity. At the singularity,
the laws of physics as we know them break down. Time and space, as we understand them, cease to function in the usual way. From the outside, a black hole is defined by its event horizon, the point beyond which nothing can escape. But what happens on the other side of that event horizon remains one of the biggest mysteries in physics. Some physicists have suggested that what we think of as a singularity may not actually be the end of the story. Instead, it might be a doorway. The crushing of matter into a singular point could cause space-time itself to bounce or bud into a new region of reality. In this interpretation, the singularity is not the final state of matter, but rather the seed of a new universe. Just as a black hole consumes matter in one universe, that energy could re-emerge in another universe as the fuel for a Big Bang-like expansion. In other words, our own Big Bang could have been the outflow from a black hole in some pre-existing universe. This idea reframes the Big Bang not as a unique beginning, but as a kind of cosmic birth cycle, where universes beget other universes through black holes. The logic behind this theory builds on the fact that black holes do strange things to space-time. Near the event horizon, time slows down relative to an outside observer, stretching infinitely at the boundary. Inside, if relativity's equations are followed to their limit, time and space effectively swap roles. That flip opens the door to the idea that the collapse of matter inside a black hole might not simply end in a timeless void, but could instead create a new temporal direction, an arrow of time pointing outward from a fresh explosion of energy. What looks like a singularity from one side could appear like a Big Bang from another. One of the most intriguing elements of this proposal is that it provides a possible mechanism for why the Big Bang happened at all. Instead of being an inexplicable starting point that erupted from nowhere, it could have been triggered by physical processes in another universe. Every black hole in that parent universe would then be a kind of cosmic womb, with each one potentially spawning its own universe on the other side. This means our universe might be just one among countless others, each born from the death throes of stars in older universes. The physicist Lee Smolin is one of the most notable advocates of this line of thought. He has proposed what is known as cosmological natural selection. In his version of the theory, universes that produce many black holes will naturally give rise to many offspring universes. Each black hole births a new universe, and the laws of physics in those offspring may be slightly different from the parent universe. Over time, through this branching process, universes that are better at producing black holes will become more common. This creates an evolutionary tree of universes, where our own might be the product of many generations of cosmic selection. If true, this means the structure of our universe, our laws of physics, the masses of particles, the strength of forces, might be tuned not for life specifically, but for maximizing black hole production. There are also deep implications for our understanding of information. One of the great paradoxes of modern physics is the black hole information problem. What happens to the information carried by matter that falls into a black hole? Quantum mechanics tells us information cannot be destroyed, yet relativity seems to imply it vanishes beyond the horizon. If black holes are connected to new universes, this could provide a radical resolution. The information might not be destroyed, but instead transferred into the newborn universe, encoded in its initial conditions. Our own universe's starting state, the distribution of matter and energy at the Big Bang, could then be the inherited imprint of information from another universe's black hole collapse. The black hole universe idea also connects with the concept of white holes, which are hypothetical opposites of black holes. A white hole would be a region of space-time where matter and energy can only flow outward, never inward. No white holes have ever been observed, but mathematically, general relativity allows for them as time-reversed black holes. The Big Bang, from this perspective, could be thought of as the ultimate white hole, a singularity that spewed matter and energy outward in every direction, creating our universe. If every black hole in one universe generates a white hole on the other side, then the cycle of birth and death of universes could be endless. However, this is still highly speculative. For one, we do not yet have a complete theory of quantum gravity that can describe what happens inside a singularity. General relativity predicts the singularity as a breakdown point, but quantum mechanics is expected to modify this picture at extremely small scales. Until those two great pillars of physics are unified, what lies inside a black hole remains an open question. Furthermore, there is no direct evidence that black holes spawn universes. The idea is elegant and compelling, but we cannot observe beyond an event horizon, nor can we detect another universe from within our own. At least, not with our current understanding of physics. Still, the concept resonates because it addresses one of the deepest puzzles. Why did the Big Bang happen? If black holes can generate new universes, then beginnings are not as mysterious as they first appear. Each Big Bang would simply be part of a larger cycle of cosmic reproduction. It also provides a context in which our universe is not special, but one of an immense branching family tree. Every time a star collapses into a black hole, it could be planting the seed of another universe, with its own galaxies, stars, and perhaps even beings asking the same questions we are. What makes this theory even more astonishing is that if it's true, the parent universe that birthed ours may itself have been born from a black hole, and that universe may have come from another, stretching back into an infinite lineage. In this framework, there may never have been a first universe, just an eternal chain of universes giving birth to universes, each one carrying the legacy of its ancestors. The Big Bang would no longer be the absolute beginning of everything, but just one chapter in an infinite saga. Of course, skeptics point out that this theory may not be testable, at least with our current tools. Without observational evidence, it sits in the realm of speculation, a grand story about existence that cannot yet be confirmed. But history shows that many ideas once thought untestable eventually found ways to be investigated. Perhaps one day, through gravitational wave signatures, black hole thermodynamics, or new breakthroughs in quantum gravity, we might glimpse clues that point toward our universe's origin inside another. Until then, the black hole theory remains one of the most captivating possibilities. A vision of universes nested within universes, each Big Bang not a beginning from nothing, but a continuation of a cosmic cycle without end. The simulation hypothesis introduces a radical possibility that the universe we inhabit, including the Big Bang itself, might not be the product of natural physical processes at all, but the result of an artificial design, a coded or programmed reality created by a vastly superior intelligence. This idea has gained traction not only in philosophy and speculative thought, but also in serious scientific circles, because it offers a potential explanation for why the universe seems so finely tuned and why its laws operate with such precise consistency. If the Big Bang marked the beginning of our universe, could it have also been the moment when the simulation was switched on? In this view, the singularity was not an explosion of matter and energy, but a computational reset, the initialization point of a complex program that we now perceive as reality. The premise stems from the question of computational power. As technology evolves, humanity has already created simulated environments, from basic cellular automata to immersive virtual worlds. While our simulations are primitive compared to the complexity of a cosmos, they prove the concept that simulated realities can exist. If a civilization were millions or billions of years more advanced than ours, their computational capabilities might allow them to simulate entire universes down to every particle, governed by a set of mathematical rules, what we call the laws of physics. In this framework, the Big Bang represents the starting conditions of that simulation, the initial parameters being booted up into existence. From that single point, the expansion of space-time
and the development of galaxies, stars, and life would all be outputs of a vastly complex program unfolding according to predetermined algorithms. One of the striking aspects of this hypothesis is how it recontextualizes the mysteries of the cosmos. The fine-tuning problem, for example, the observation that constants like the strength of gravity or the charge of the electron seem just right for life to exist, might not be a coincidence at all, but the result of design. A programmer could set the constants as inputs, ensuring that conditions for complexity and consciousness would arise within the simulation. In this sense, the Big Bang wasn't random, but intentional. The starting point chosen to allow for the unfolding of a universe capable of evolving intelligent beings who could eventually question their reality. From a physics perspective, some argue that phenomena like quantum mechanics hint at the possibility of a simulated framework, the way particles exist in superposition until observed, or how probabilities collapse into specific outcomes, seems strangely similar to the way information in a video game only fully renders when a player's perspective requires it. In this analogy, reality doesn't need to compute every detail until there is an observer to interact with it. Could the Big Bang itself be analogous to pressing start on such a simulation, with quantum uncertainty being the underlying code dictating its behavior? If this is true, the question of what was before the Big Bang changes dramatically. Instead of pondering pre-cosmic physics or alternate universes, one might ask, who or what programmed it? The before could exist outside our universe entirely, in a higher-level reality where beings, whether biological, artificial, or entirely beyond our comprehension, engineered the cosmos as an experiment, a story, or even entertainment. Our universe would then be just one of countless simulations running in parallel, each beginning with its own Big Bang initialization sequence. The multiverse, in this sense, becomes not a collection of naturally occurring bubble universes, but a network of artificial constructs, each spun up by creators in a more fundamental reality. Critics of this idea raise significant objections. For one, the simulation hypothesis is notoriously difficult to test. If we are in a simulation, then all our attempts to measure it would be taking place within the constraints of that simulation. The evidence we would find, whether anomalies in physics or irregularities in cosmic background radiation, might themselves be simulated outputs, carefully controlled by the system. However, some have proposed possible indicators. For example, if space-time is not continuous but pixelated at the smallest scales, like the grid of a computer screen, we might detect limits in resolution at the Planck length. Likewise, unusual alignments or patterns in cosmic background radiation could, in theory, resemble glitches in a rendered environment. These remain speculative, but they represent attempts to approach the hypothesis scientifically.
Another objection is philosophical. If we are simulated, does it matter? Our lived experiences, emotions, discoveries, and struggles would still feel real to us. The Big Bang, even if it was a code start rather than a cosmic birth, would still be the origin of our reality as we know it. Yet, the implications are profound. If a simulation can be ended or altered at the will of its creators, then the ultimate fate of our universe may not be governed by heat death or cosmic collapse, but by external intervention, a shutdown. Similarly, it redefines existential questions. Are we free agents, or are our choices part of the programmed code? Is consciousness an emergent property of complex information processing, or was it deliberately embedded by designers? What makes the simulation hypothesis compelling in discussions about what came before the Big Bang is how it reframes the problem entirely. Instead of infinite regress, universes before universes, cycles upon cycles, it posits a higher plane of reality where the rules of our cosmos no longer apply. It suggests that the mystery of before might lie not in physics but in metaphysics, not in cosmology but in computation. The Big Bang, then, becomes less of a natural singularity and more of a programmed initialization sequence, a moment when zeros and ones cascaded into existence, giving rise to galaxies, stars, and life. Whether one sees it as unsettling or awe-inspiring, the simulation hypothesis expands the horizon of possibility. It challenges the assumption that the universe must be real in the way we intuitively think of reality, and it forces us to confront the limits of human understanding. If true, it would mean that asking what was before the Big Bang is akin to asking what was happening before the game was launched. The answer lies outside the system, in a domain we may never be able to access directly. And yet, the very fact that we can conceive of this possibility might itself be part of the purpose. Perhaps the creators wanted their simulated beings to question, to wonder, and to seek answers beyond the confines of their programmed cosmos. There is a school of thought that sidesteps the very notion of a beginning altogether. Instead of treating the Big Bang as a unique birth event, these ideas propose that the universe has always existed in some form, eternal, uncreated, and without origin. At first glance, this might sound like a philosophical stance rather than a scientific model, but several cosmological theories lend weight to the possibility of an eternal cosmos. They don't all imagine the same eternal structure, but they share the refusal to accept absolute creation from nothing. One of the earliest inspirations for this idea comes from the ancient philosophical notion that nothing comes from nothing. If matter, energy, and space truly cannot emerge spontaneously, then perhaps the cosmos never had a true beginning. It has simply always been here, cycling, transforming, and changing, but never ceasing. In physics, this principle has echoed through models that resist singularities. Rather than imagining a sharp boundary where time begins, these models extend infinitely backward and forward. A famous version of the eternal concept is the steady-state model, proposed in the mid-20th century. According to this idea, the universe expands as we observe, but new matter continuously forms to fill the gaps, keeping the large-scale structure roughly the same forever. This would mean no Big Bang in the traditional sense, just an endless, eternal universe stretching across time. Though eventually disfavored due to the overwhelming evidence for a hot, dense beginning, such as the cosmic microwave background, steady-state cosmology is still remembered as an important attempt to preserve eternity in physics. Modern eternal models take more sophisticated forms. Some theories in quantum cosmology suggest that the Big Bang was not the beginning of everything, but simply a transition between states. For example, certain interpretations of loop quantum gravity propose that instead of a singularity, the universe bounces at extreme densities, meaning that a contracting phase always precedes an expanding one. This creates an infinite chain of universes, each with its own expansion and contraction, eternal in both directions of time. Another angle comes from inflationary theory. Eternal inflation is often discussed as spawning countless bubble universes, but one subtle implication is that inflation itself may have no beginning. The inflating background could stretch infinitely into the past as well as the future, with bubbles like our universe budding off eternally. If true, this would mean our Big Bang wasn't the first or last, but just one event in an unending cosmic process.
Then there are models inspired by thermodynamics and entropy. In a closed system, entropy, the measure of disorder, always increases, which seems to rule out an eternal universe, since an infinitely old cosmos should already be maximally disordered. Yet, some theories suggest ways around this. For example, if entropy can reset through cosmic contractions, or if new low entropy regions constantly emerge, then time can stretch back infinitely without violating the second law. The idea here is that while parts of the cosmos may run down, new ordered regions can sprout eternally, giving the universe an endless regenerative cycle. From a different perspective, string theory hints at a possible eternal structure. In certain formulations, the fabric of reality consists of fundamental strings or higher dimensional branes that exist timelessly. Collisions between branes might trigger Big Bang-like events, but the branes themselves would exist forever. meaning that the universe, in some higher dimensional sense, never had a true beginning. In such a picture, the Big Bang is simply a local flare-up in an eternal framework. Of course, the eternal universe raises its own profound questions. If the cosmos has always existed, why does it appear the way it does today? What mechanism preserves its structure against entropy's decay? Can we reconcile eternal time with quantum mechanics, which seems to favor beginnings and transitions? These challenges keep the eternal models speculative but fascinating. What's striking is that the eternal approach resonates with human intuition in a way that other models often don't. The idea of an absolute beginning, a sudden creation from nothing, feels counterintuitive to many. By contrast, an eternal cosmos aligns with the sense that existence must always have been. It echoes ancient mythologies that describe the universe as endless, uncreated, and indestructible. Even modern cosmologists sometimes admit a certain elegance in bypassing the problem of origins by removing the need for one altogether. If the universe truly is eternal, then our Big Bang was not the beginning of everything, but simply one chapter in an infinite book. What came before? More universes, more cycles, more expansions and contractions stretching endlessly into the past. What comes after? The same, without end. An eternal cosmos does not solve every mystery, but it changes the question entirely. Instead of asking how everything began, we are left asking how eternity itself is structured, and whether we can ever hope to glimpse its full scope. The idea of a quantum tunneling origin for the universe is one of the most fascinating and deeply perplexing proposals in modern cosmology, because it asks us to consider that everything, space, time, energy, matter, even the very laws of physics themselves, might have spontaneously emerged through a purely quantum mechanical process. At its heart lies the principle of quantum tunneling, a phenomenon that, while strange, is already well documented in the world of particles and atoms. In quantum mechanics, particles don't follow classical rules of motion. Instead, they are described by probabilities, existing as waves of potential outcomes. This means that even if something appears to be impossible according to classical laws, in the quantum realm, there is always a chance, however small, that it can occur. A particle can tunnel through an energy barrier that it could never climb over using traditional physics, simply by exploiting the probabilistic uncertainty at its core. Now, take that concept and scale it up from the microscopic to the cosmic. The idea of quantum cosmology suggests that the universe itself may have originated from such a tunneling process, in which nothing was not truly an empty void, but rather a quantum state, a kind of undefined, pre-geometric condition where no space or time existed in the way we understand it. In this strange and incomprehensible quantum vacuum, fluctuations could occur, and one of those fluctuations might have tunneled into what we now call existence, creating an expanding universe. The Big Bang, in this sense, wasn't the explosion of something into space, but the quantum tunneling of a universe out of nothingness, or at least out of a state that transcends what we call something and nothing. This is the basis of models such as those proposed by physicists Alexander Vilenkin and Andrei Linde. Vilenkin, in particular, has argued that the universe could have tunneled into being spontaneously, without cause, purely as a quantum event. Just as a particle doesn't need an external push to tunnel through a barrier, the universe may not have needed an external trigger to spring into existence. In his framework, the laws of quantum mechanics themselves provide the foundation, allowing universes to appear, vanish, and expand. The incredible implication is that existence may not require an initial mover, creator, or prior cause. Instead, the rules of probability could have been sufficient to set everything in motion. Of course, this raises deep philosophical and scientific challenges. For one, what does it mean for the laws of physics to exist before the universe? If space and time were created in the Big Bang, then how can the rules of quantum mechanics predate the cosmos?
Some theorists suggest that the laws of physics are not bound to the universe itself, but are abstract, timeless principles that exist independently. Others argue that these laws might be emergent, that they only make sense within a universe, and the very concept of laws before the universe might not be coherent. This tension between physics and metaphysics lies at the heart of debates about quantum tunneling origins. Still, mathematical models offer intriguing insights. One of the most famous is the Hartle-Hawking no-boundary proposal, which suggests that the universe is finite but without a boundary, much like the surface of a sphere. In this view, the universe could tunnel into existence smoothly without a singularity, gradually transitioning from a timeless quantum state into the expanding cosmos we observe today. It's not that time stretches infinitely backward, but that the universe emerged from a timeless, pre-space-time condition. Quantum tunneling provides the mechanism, bridging the gap between nothing and something without requiring an infinite regress of causes. Another fascinating implication of quantum tunneling origins is the possibility of a multiverse. If universes can emerge spontaneously through quantum processes, then why just one? Just as quantum mechanics allows for countless possible particle behaviors, it may allow for countless bubble universes to tunnel into existence, each with its own physical laws and constants. This vision paints reality as a vast sea of possibility, where our universe is only one realization among an infinite set. In this sense, the Big Bang might not be a unique event, but a natural, inevitable outcome of quantum rules at play on a cosmic scale. Skeptics point out that while quantum tunneling is a well-established phenomenon at the particle level, extrapolating it to the creation of an entire universe stretches beyond current scientific validation. We cannot run experiments to observe universes popping into being, nor can we measure what nothing truly means. Yet, quantum mechanics has consistently proven to defy intuition, and many of its strangest predictions have been confirmed in laboratories. To dismiss the idea outright would be premature, especially when it offers a plausible explanation for one of the deepest mysteries of existence: why there is something rather than nothing. Philosophically, the quantum tunneling idea pushes us to reconsider causality. Our human intuition demands causes for events. The domino falls because another domino pushed it. A planet moves because of gravity. A match lights because of friction. But at the quantum level, events can happen without deterministic causes, governed only by probabilities. If the universe's birth was such an event, then perhaps asking what caused it is the wrong question. It might be that existence is the result of a probability wave resolving into reality, with no deeper cause needed. This leaves us in an extraordinary position. The quantum tunneling origin model suggests that the universe may have appeared spontaneously, that time itself began in that instant, and that no external force or pre-existing structure was necessary. It strips the question of ultimate origins down to its most minimalist answer: existence arises because it can. And yet, in doing so, it provokes even deeper questions. Why do the rules of quantum mechanics exist at all? Why do probabilities permit universes rather than only particles? What does it mean for timelessness to give birth to time?
The idea of quantum tunneling origins doesn't close the mystery of the Big Bang. It amplifies it. It provides a physical mechanism for how something could arise from a timeless, causeless state, while simultaneously leaving us with the profound enigma of why such a mechanism exists in the first place. In the end, it captures the spirit of all cosmological speculation, a balancing act between the rigor of physics and the awe of philosophy, an attempt to reach into the unknown and find coherence in the most incomprehensible question of all: how did it all begin? The question of energy conservation in the context of the Big Bang is one of the most fascinating and perplexing puzzles in cosmology. In our everyday lives, we are taught that energy cannot be created or destroyed, only transformed from one form to another. This principle, known as the law of conservation of energy,
underpins everything from how machines work to how biological systems sustain themselves. But when it comes to the origins of the universe, this seemingly inviolable law runs into a wall of ambiguity. Did the energy that powers stars, fuels galaxies, and makes up everything we see always exist in some form before the Big Bang? Or did the Big Bang represent the actual moment when energy itself first came into being? One school of thought leans toward the idea that energy has always existed, simply reshaped and reorganized during the Big Bang into the form we observe today. From this perspective, the Big Bang wasn't the creation of energy from nothing, but rather the transformation of a prior state of reality into a new form. This would align with models such as oscillating or cyclic universes, where a collapsing universe could funnel its matter and energy into a singularity, only to rebound as a new expanding cosmos. In this sense, energy is eternal, neither lost nor born, but instead endlessly recycled through cosmic cycles. However, another view suggests that the Big Bang represents the actual birth of energy itself. This ties into quantum theories, particularly the role of vacuum fluctuations. In the strange world of quantum mechanics, particles and energy can spontaneously appear and vanish in empty space due to uncertainty principles. Some physicists propose that the universe's total energy might have emerged this way, essentially as a quantum fluctuation magnified to cosmic proportions. If this is true, the Big Bang wasn't just the rearrangement of existing energy, but rather the spontaneous emergence of all energy from a kind of primordial quantum state. This leads to an even deeper debate about what we mean by energy conservation on a universal scale. In physics, the conservation of energy is tied to time symmetry, the idea that the laws of physics don't change over time. But if time itself began at the Big Bang, can we really apply the concept of energy conservation before that moment? Some argue that because time did not exist before, there was no stage on which energy conservation could operate. In this view, the Big Bang might not have violated conservation. It may have been the moment when the rules of conservation first came into being. Adding another layer of complexity is the idea that the universe's total energy may actually balance out to zero. Matter and radiation carry positive energy, but gravity carries negative energy. If the two balance perfectly, the net energy of the universe might be nothing at all. This so-called zero-energy universe hypothesis suggests that the Big Bang didn't need to conjure energy from nowhere, because, in a cosmic accounting sense, there is no net energy to explain. The universe may simply be a vast balance sheet where everything cancels out. These possibilities open profound philosophical questions as well. If energy always existed, does that imply an eternal universe that defies beginnings and endings? If energy was created at the Big Bang, what does that say about causality and the ultimate origin of the laws of physics themselves? And if the universe's net energy is zero, could the entire cosmos be seen as a grand illusion of somethingness, arising from nothingness, perfectly balanced yet infinitely real to us?
The energy conservation debate is not just about equations, it's about the boundaries of what science can explain. Our physical laws are reliable guides within the universe, but at the edge of the beginning, they may bend, transform, or even fail altogether. Whether energy has always been there, emerged at the Big Bang, or exists in a perfect balance of opposites, each interpretation pushes us closer to understanding the mystery of why there is something rather than nothing. It reminds us that the Big Bang is not merely a story of expansion and galaxies, but also a story about the very essence of existence itself. The closing reflection on the question of what was there before the Big Bang is perhaps the most humbling part of the journey. For every theory, from quantum fluctuations to eternal cycles, from brain collisions to the hypothesis of nothingness, we circle around the same profound truth. The beginning of everything we know is still wrapped in mystery. Science gives us models, mathematics gives us frameworks, and philosophy gives us questions, but none of them settle the matter once and for all. We peer back through telescopes, simulate universes in supercomputers, and stretch human thought to its very limits. Yet when we approach that singular moment, the dawn of time itself, we find ourselves standing before a horizon we cannot yet cross. Perhaps what came before is not meant to be known in the way we usually understand knowledge. It could be that time itself, the very fabric through which we measure cause and effect, begins at the Big Bang, making the idea of before meaningless. Or it could be that reality is far larger, stranger, and more interconnected than we imagine, with other universes, other timelines, or hidden structures that our current tools cannot yet detect. Each theory opens a door to possibilities, but also leaves us facing the vast unknown. And maybe that is the true gift of the question. Not the answer, but the endless pursuit. The act of asking what was before the Big Bang forces us to look beyond what is comfortable, beyond what we can see, and into realms where imagination and reason intertwine. Every attempt to solve this riddle expands the boundaries of human thought. Every hypothesis, whether proven or not, deepens our appreciation of the cosmos. It reminds us that existence itself is astonishing, that we live in a universe capable of stars, galaxies, and life, emerging from conditions so extreme we struggle to describe them. And it reminds us that we are a part of this unfolding mystery, not outside it. Our curiosity is itself a product of the same cosmos we are trying to understand, an echo of the very processes that gave rise to space and time. Perhaps one day, through new physics or unimaginable discoveries, we will glimpse further into that hidden realm. Or perhaps the question will always remain just beyond reach, a reminder of our limits and our smallness before the infinite. Yet even then, the pursuit itself is a triumph. Because in chasing the origins of everything, we uncover not only the nature of the universe, but the essence of what it means to be human, seekers of truth in a cosmos that forever invites us deeper. The greatest mystery of all may be that we will never know what came before, but in asking, in exploring, in daring to reach beyond the edge of time, we expand not only our understanding of the universe, but the universe of our own minds. And maybe that is the real beginning, one that continues with every question we ask, every horizon we chase, and every moment we choose to wonder. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.